Hi, my name is Rebecca Holman, and my presentation is going to be on concrete. When you talk about concrete, you're inherently talking about cement as well, because you can't make concrete without cement. So this presentation is a little bit of a mix between talking about concrete and cement. So cement is a blend of a variety of raw materials: calcium, silicon, aluminum, and iron. The most common type of cement is Portland cement, which is actually named after where the limestone is mined. Cement has adhesive qualities that bind well to many different surfaces, which is why it's such a good material, is its ability to bind. But it's typically prone to cracking and not suitable for large jobs. However, when cement is mixed with water, it creates a paste. And then once aggregates like sand, stone, rocks, gravel, etc. are added to the mix, that is when it then becomes concrete. This process is an exothermic reaction and is called the heat of hydration because heat actually emanates from the concrete during this process. The generic ratio for concrete is usually 1 part cement, 2 parts sand, and 3 parts aggregate. Adding water to it holds it all together until it hardens. And the strength of the concrete is directly related to the amount of water added. So adding a lot of water will make the compound easier, more malleable to use, and adding less water, which makes it less workable, will make the finished product stronger and more durable. Concrete is the world's most widely used material for construction. And, we see it everywhere in every aspect of our life: buildings, bridges, etc. Over 70% of the world's population lives in a concrete structure. And due to the durability and strength of concrete, it is used to build all sorts of various types of structures: pipes, floors, beams, pillars, pavement. With about 10 billion tons of concrete produced every year, it's the most consumed substance in the world, second only to water. Making cement is a really energy-intensive process. It requires raw materials like clay and limestone to be heated to more than 2,500 degrees Fahrenheit to turn them into the binding agent. Unlike other major construction commodities, concrete produces carbon emissions in 2 ways, not just one. The first way is actually the power required to run the plants to produce the concrete, because that electricity and heat is still overwhelmingly comes from burning fossil fuels. Second, the actual chemical process itself, calcination, produces a significant amount of carbon dioxide as a byproduct. Roughly 1,300 pounds of carbon dioxide is produced for every metric ton of cement manufactured. Cement production requires a large amount of energy use, but in addition to that, the smaller ingredients that make up the aggregate of concrete, like sand and stone, come from mining, natural resources, and susceptible habitats. Concrete also has a high demand for fresh water, making up about 20% of the world's industrial water consumption. Here you can see the LCA breakdown flows of cement. So you can see the inputs, the raw materials, energy, and water, all of the different flows, and then the carbon dioxide and air emission outputs. In contrast, here's the LCA for concrete, which again has raw materials and water and energy input. But for concrete, most of the life cycle analysis focus is in the cement production up here. Concrete is the second most widely used substance on Earth, behind only water. The cement sector is the third largest consumer of energy and the second largest emitter of carbon dioxide when considering industrial industries. Scientists say that the cement industry needs to decrease its annual emissions by 16% in order to align with the Paris Agreement. However, between 2002 and 2021, global emissions doubled from 1.4 billion tons of CO2 to 2.9 billion tons. Cement manufacturing accounts for 8% of all of the world's CO2 emissions. For comparison, aviation, so all flights, so the aviation industry is only 2.8% of the world's global emissions. So cement is triple that. Because of its widespread use and large CO2 emissions, the impacts of concrete are astronomical. So what can we do about it? Fortunately, there are already many alternatives to concrete on the market and even more in creation as we speak. The first option, green concrete, is essentially a form of eco-friendly concrete that is manufactured using waste materials or residual materials from different industries. So this would require less amount of energy for production compared to traditional concrete, produces less carbon dioxide and is significantly cheaper. The aim of using green concrete is to lessen the burden on natural resources and increase recyclable materials. One of the main strategies for green concrete is to reuse wash water to reduce water consumption in concrete production. Partial replacement of energy-consuming cement with reusable materials is one of the best strategies. For example, cement can be replaced with fly ash, silica, wood ash, etc. Fly ash is a byproduct of the combustion of coal, which was previously discarded in landfills but is now used for manufacturing green concrete. There is one product on the market called ashcrete, which is a substitute using recycled fly ash. Fly ash is mixed with lime and water to make it strong and durable, and it's very similar to conventional cement. Another option is using microsilica. This is called silica fumes. Microsilica is ultrafine powder, which is the byproduct of silicon production. And this can displace around 12% of cement and concrete. Microsilica also is less permeable and comparable in strength. There's other ways to substitute for cement, like replacing aggregate materials with other reusable resources. So the second way, and first, the green concrete is replacing cement with recyclable materials as much as possible. Second way is aggregate replacement. So in addition to cement, concrete is made up of aggregates like sand, stone, rock, etc., and water. So this is trying to find ways to replace the sand, stone, aggregate materials. These can be replaced by paper or fiber, recycled plastic, post-consumer glass, etc. So papercrete is a product on the market which uses waste paper in replace of aggregates. It doesn't entirely replace the mixture, but it's enough to combat some of the ill effects of concrete production. Glass is another suitable aggregate replacement for concrete. It can be recycled and reused many times without any changes to its chemical properties, so it actually increases the durability of the concrete. And another way is to utilize waste plastic because it's a non-biodegradable material. Plastic waste can be easily recycled and can replace up to 20% of the traditional aggregate material. Although concrete produced using plastic waste provides strength to a specific limit, it is unarguably an eco-friendly alternative to traditional concrete. The third is hempcrete, which is a relatively new biodegradable alternative entirely to concrete. It's made of hemp fibers mixed with lime and water, which creates a concrete-like material, but it's lighter and stronger. Lime releases about 80% less carbon as compared to traditional cement. So hempcrete can actually be considered carbon negative. It provides natural insulation and flexibility to the structure. However, one of the drawbacks is it can't be used in load-bearing walls. And the last alternative solution is to adapt buildings to use less concrete and cement. The problem is concrete is cheap and versatile. It doesn't need fireproofing. So this is only feasible depending on the building's location. Natural disasters like earthquakes can still devastate buildings with minimal concrete, so would it take careful design consideration to make new structures with even less concrete. Unfortunately, there's an increasing human population, which means there's an increasing need for infrastructure and therefore more concrete. As there becomes more of a push for alternative solutions to concrete and cement manufacturers might try to skirt around new potential implementations by paying or by using carbon capture as an easy way out. California, for example, is relying on carbon removal technologies to achieve much of the state's mandatory emission reduction targets. For many industrial sectors, most importantly cement manufacturing. But many people have said that these carbon removal technologies are expensive, difficult to scale, and distract from proven solutions like just switching to renewable energy sources. Lastly, because concrete is so widely used, durable, long-lasting, and weight-bearing, potential alternatives might have limited uses depending on their strength and durability. Thank you guys for listening.